In this video, we learn about the infinite sum of a geometric sequence. More specifically, we learn about converging geometric series. And to do that, we're going to start with the example sequence we see here. We have a geometric sequence whose first few terms are 4, 2, 1, 0.5, and it carries on forever this way. As one should always do when working with geometric sequences, let's make a note of its first term, that's 4, as well as its common ratio. Remember, the common ratio is the amount we have to multiply each term by to get to the next term. And if you can't see what that number is right away, you can always find the common ratio by taking any term of the sequence and dividing it by the previous term. So we could do 0.5 divided by 1, or 1 divided by 2, and of course we could do 2 divided by 4. And it doesn't matter which of those you choose to use, they'll all lead to the same answer. And so let's see, I'll say that the common ratio r is equal to, well, I'll take the third term divided by the second. So that would be 1 over 2, which we could also write as a decimal as r equals to 0.5. There we go, that's the common ratio taken care of. And of course, as I said a minute ago, we should always make a note of the first term as well. So we can also write u sub 1, or u1, equals to 4. There we go. And I can write a little times 0.5 here in between each of these terms. There. Okay, now as I said at the very beginning, here we're going to be learning about the infinite sum of a geometric sequence. And here's the whole idea. Underneath this geometric sequence, I'll go ahead and write its corresponding geometric series. Remember, given a geometric sequence, its geometric series is another sequence of numbers whose nth term is equal to the sum of the first n terms of the sequence. Here's what I mean. The first term of the geometric series is equal to 4, which is the same as the sequence. The second term of the geometric series will equal to the sum of the first two terms of the geometric sequence. So that's 4 plus 2, which is 6. I carry on. The third term of the series will equal to 4 plus 2 plus 1, the sum of the first three terms of the sequence. And 4 plus 2 plus 1, well, that's equal to 7. And I carry on this way. The fourth term in the series will be 4 plus 2 plus 1 plus 0.5, which will be 7.5. And I'll carry on with this series in a bit, but let me just stress the fact that the terms of a geometric series correspond to the sum of the terms of the geometric sequence. So the fourth term in the series corresponds to the sum of the first four terms of the sequence. The second term in the series corresponds to the sum of the first two terms of the sequence. And the 10th term in the series, well, that would correspond to the sum of the first 10 terms of this sequence. Now, you can go ahead and check, but if we look for the next three terms in this sequence, the next one would be 0.25, followed by 0.125, followed by 0.0625. And we could go on this way, but I'll stop there. And now using these additional terms inside our sequence, we can find the corresponding terms in the series. And so for the fifth term of the series, we'd have to add the 0.25 here, so that would be 7.75. For the next term, we'd add a further 0.125, and that would equal to 7.875. Finally, for the next term, we'd add the 0.0625, which would give us 7.9375. And again, we could carry on forever that way. Now, looking at the terms of this geometric series, the difference between the terms is getting smaller and smaller and smaller. And that makes sense because the terms in the sequence are getting smaller and smaller and smaller. So from one term to the next, we're adding less and less and less. Secondly, the terms that we have here seem to be getting closer and closer to 8. And here's the thing. You could spend your entire day writing as many terms as you possibly can inside this geometric sequence, to then find all the corresponding terms of the geometric series, and the terms in the series would never actually reach 8. And that's regardless of how many more terms in the sequence you write. We say that this geometric series converges towards 8. And another way of saying that, which is in the title of this video, is that the terms of this geometric sequence have an infinite sum. And you may also hear the term total sum. And the infinite sum is written as capital S sub infinity, and it's equal to the first term of the geometric sequence divided by 1 minus the common ratio r. And I'll go ahead and box that. Do make a note of this. And on the side here, I'll write infinite sum. And now going back to our example here, if we use the formula we just wrote, we could go ahead and state that its infinite sum, s sub infinity, is equal to the first term, u1, over 1 minus r. And so that will equal to 4 over 1 minus 0.5, which turns into 4 over 0.5. And by all means check with the calculator if needs be, but 4 divided by 0.5 is equal to 8. So we can state that s sub infinity is equal to 8. Done. What this value represents is the number the sum of all the terms in this geometric sequence will get closer and closer and closer to. Another way of saying that is that this infinite sum is the number that the terms in this geometric series converge to. But now there's a catch. Not all geometric sequences have an infinite sum, and consequently, this formula can only be used for certain geometric sequences. And here's the deal. Looking back at our sequence here, its common ratio was 0.5. And the fact that it's equal to 0.5 meets the condition for a geometric sequence to have an infinite sum. And that is that its common ratio has to lie between -1 and 1. And I'll write that at the top here. I'll say if the common ratio r is between -1 and 1, then the geometric series, and therefore the sum of the terms of the geometric sequence, converges towards s infinity. Converges towards s sub infinity. Done. And in fact, I'll box that as well. There we go. That's the condition for a geometric sequence to have an infinite sum. Or I could say, this is the condition for a geometric series to converge towards this value. Careful, if ever this condition isn't met, for instance, if ever r were equal to 3 or -5 or 10, then the geometric series, and therefore the sum of the terms of the sequence, diverges. Okay, at this stage we know the condition for a geometric series to have an infinite sum, and we know the formula for the infinite sum, and we showed how to use it for the sequence we have here. And in a minute I'll show you why this is the formula for the infinite sum. Before doing that though, let me go back to this example and discuss it a little further. When I first learnt about this topic, I found it really troubling. And the reason why this bothered me, I found it hard to believe that I could spend my entire life adding more and more terms of the sequence together, and therefore obtaining more and more and more terms of the geometric series, but that the sum could never exceed a given number, like this one here, 8. And at the time I found it really fair to ask, how is that possible? How can I keep on adding on to numbers like this one for days and days and days if needs be without ever reaching 8? And I think I used to think of this a bit like this. I'd have a cup of water, or a glass of water, and let's say that every second that went by I let a drop of water fall inside the cup. Then, as I'm sure you'll agree, little by little this cup will begin to get filled up. And eventually, when enough of these drops fall, the cup will overflow. And so when I thought about this geometric series, or the sum of the terms of this sequence, I had trouble seeing how I could keep on going in this sequence adding more and more and more terms without ever reaching 8. Since in my mind, it was the same as little drops of water falling into this cup, which will eventually overflow. But here's the thing, it's not like this cup. And so for the sake of really understanding why this type of sequence converges towards a number, in this case 8, let me illustrate this sequence. Let's say I have an 8-meter ruler, which I'll draw like this. There we go. And so I'll say this is 0, and this is 8. And let's say we have a little particle, something like this, which is initially placed right here. And then I tell you, after each minute that goes by, you can move this particle half the distance that separates it from the other side of the ruler. So, since the total distance is 8 meters, after 1 minute we'll be able to move this particle 4 meters across. And so that would be in the middle, right here, and I'll draw the particle here. There we go. And so we're now 4 meters across the ruler. And so I'll write a 4 here, And I'll also draw the step size right here. So for that first step, we moved 4 meters. Then after 2 minutes, we can move this particle half the distance that separates it from the end again. And this time, because there's only 4 meters left, and since half of 4 is 2, it would lead us to this position here that's 6 meters along. And so I place my particle there, like so. Now this time round, the step size is 2 meters. And I carry on this way. After the 3rd minute runs up, we can move half the distance that separates this particle from the end of this ruler, which would be right here at 7 along the ruler, and I've got to have my particle here, and this time the step size is 1 meter. I carry on just a little longer. After the 4th minute, I move this particle half the distance that separates it from the end of the ruler, which would be right here at 7.5, and now the particle is right here. And the step size, well, that's 0.5. And although it's now getting difficult to draw this, I'll move the particle one last time in this illustration. After the next minute is up, I move this particle half the distance that separates it from the end, which would lead it to here, and that's 7.75. And the particle would be here, and the step size is 0.25. Now here's the thing. At the bottom of the ruler here, the numbers we see correspond to the geometric series. 4, 6, 7, 7.5, 7.75, and so on and so forth. Indeed, those are the numbers we had right here. At the top of the ruler, on the other hand, the step sizes, well, those are the terms of our geometric sequence. And the fact is, this particle will technically never reach the end of this ruler. And the reason for that is because we're only ever allowed to displace it by half the distance that separates it from the end. So there'll always be a gap between the particle and the end of the ruler, regardless of how small that gap gets. And it gets very, very, very small. Indeed, we could spend the entire day zooming in and in again on the end of the ruler here, and eventually the amount by which we displace this particle would start to look like this, 0.0000001. And the total distance traveled by the particle, which remember corresponds to the sum of the terms of the sequence, and therefore the terms of the geometric series, would eventually look like this, 7.999999999. And even with numbers like these, we could still zoom in further and end up with step sizes with even more zeros, and the sum would just end up having more and more 9s over here. But it would never actually reach 8. Now one could argue that eventually we end up with so many 9s in the decimal places that the number we'd be faced with would, for all practical purposes, be infinitely close to 8. And that's exactly what's meant when we say that the geometric series converges towards this number. It gets infinitely close to it. And so hopefully this illustration helped you understand why the sum of the terms of this geometric sequence converges towards this number. And before I erase this cup with the drop of water falling into it, let me point out that what was wrong in comparing this cup that's being filled with drops of water to a geometric sequence like this one is the fact that in my reasoning, these drops weren't getting any smaller. Indeed, when I came up with this example, I was just thinking of something very small being added each time. In this case, a drop being added again and again and again, which technically is an arithmetic sequence. And the sum of the terms of an arithmetic sequence will always diverge, which is why this cup of water will eventually overflow. That being said, I'll erase this. Okay, now before looking at one more geometric sequence, let me spend a couple of minutes to explain how we obtain this formula. And I'll just write explanation up here, explanation. Okay, now we've already seen that given a geometric sequence, the sum of its first n terms, which we write s sub n, is equal to its first term, u1, times in parentheses 1 minus r raised to the power of n over 1 minus r, where r is the sequence's common ratio. Now, if the common ratio lies between -1 and 1, which remember is the condition that we boxed up here, then the power of r that we have, so then r raised to the power of n, will tend towards 0 as n tends towards positive infinity. Now what this is actually saying is that for large enough values of n, this r to the power of n becomes negligible. And to convince yourself of that, you can go ahead and use your calculator and calculate 0.5 raised to the power of 10, or even 0.5 raised to the power of 30. And of course you could go further, 0.5 raised to the power of 1,000. And you'll quickly see that the result you get gets very close to 0. Indeed, for these you'll get 0.0000 something. And the higher you make the power, in other words, the more terms of the sequence you add together, the closer this term gets to 0. And if r raised to the power of n tends to 0, then 1 minus r to the power of n, which is what we have in the parentheses in this formula here, will tend towards 1. And that makes sense because if r to the power of n tends towards 0, 1 minus r to the power of n, well, tends towards 1 minus 0, which is 1. And so provided the common ratio lies between -1 and 1, for large enough values of n, this entire formula, s sub n, will tend towards u1 times 1, which is just u1, over 1 minus r. And that's exactly what we define as s sub infinity, which is the formula we saw earlier on. All that being said, let's quickly look at one more geometric sequence. And in fact, let me just box this explanation here to separate it from the rest. There we go. Now let's say our second geometric sequence has terms 40, 8, 1.6, and so on and so forth. And let's say we're asked to find its common ratio, to state whether or not it has an infinite sum or a total sum, and if it does, to find its value. Well, let's see. For its common ratio, remember, we can take any term of the sequence and divide it by the previous term. So 1.6 divided by 8, or 8 divided by 40 here. And I'll opt for the second option here, and I'll say that the common ratio r is equal to 8 over 40. Now, you can go ahead and check with a calculator if needs be, but 8 and 40 have a common factor of 8, and so I can write that this is 8 times 1 over 8 times 5. I can cross out the common factor and state that the common ratio is equal to 1 over 5, which I could also write as a decimal as r equals to 0.2. There we go, that's the common ratio found. And whether or not we're asked, we should always make a note of the first term, u1, which in this case is equal to 40. And I'll go ahead and box that as well. There we go. Okay, now does this geometric sequence have an infinite sum? In other words, does the geometric series we get from this geometric sequence converge? And the answer is yes, indeed. Since r is equal to 0.2, which is between -1 and 1, we can state without any further justification that this sequence must have an infinite sum. In other words, the geometric series must converge. And so we could write something along the lines of 0.2 is greater than -1 and less than 1, which implies that the sequence has an infinite sum. Sequence has an infinite sum. Finally, since this geometric sequence has an infinite sum, let's go ahead and calculate it using our formula. And so we can state that the infinite sum, s sub infinity, is equal to u1 over 1 minus r. And now replacing u1 by 40 and r by 0.2, this turns into 40 over 1 minus 0.2, which becomes 40 over 0.8. Finally, using a calculator if needs be, we find that 40 divided by 0.8 is 50, and so the infinite sum, s sub infinity, is equal to 50. And that's this geometric sequence's infinite sum. And so remember, provided a geometric sequence has a common ratio between -1 and 1, the sum of its terms will converge towards a number which we call s sub infinity, which is equal to the first term divided by 1 minus r. And there we go. That's it for this tutorial.